My name is Shuwei. Thank you for coming to hear my seminar. Um, so the topic of my thesis is explaining synthesized pathfinding heuristics via iterative visualization and modification. So I would like to thank my supervisor, Vadim Beliko, and William Yu from the United States. They both contributed to this project. And the parts of the thesis is published in this published work in IEEE Conference on Games. There are two related works. One is for synthesizing priority planning formulae for multi-agent pathfinding, and the other is for synthesizing single-agent heuristics for A-star search. And I would like to thank INSERC for the funding and DRAC, so Digital Research Alliance of Canada. It used to be called Compute Canada for the computing resources. And here's the presentation structure. I'll start with the motivation, and I'll talk about the background and the problem setup. Then I'll do a brief survey of some related work. Then I'll introduce our proposed approach to explain the synthesized formulae. And then I'll go over a few case studies of how our method works. And then I'll go over the empirical study and ending with future works and conclusion. So first of all, motivation. Why do we want to explain synthesized heuristic formula? Or why do we even want to synthesize heuristic formula in the first place? Previous works have shown that program synthesis is beneficial for search. We have work that show empirically that program synthesis can synthesize great heuristics for single-agent pathfinding and great priority planning formulae for multi-agent pathfinding. And one of the promises of symbolic heuristic formula is that it can be explainable. So our goal today is to explain a synthesized heuristic formula to a human user. And furthermore, after explaining it to a human user, the human user can use this explanation can utilize this explanation to improve the synthesized formula so that we can foster a human-computer collaboration. So I'll go over the background now. First of all, pathfinding. So pathfinding problem is composed of a graph and a star state and goal state. So here's our graph. Usually, the black cells represent walls and white cells represent empty spaces. But here we do the opposite. The white cells represent walls here, and the black cells represent empty space. And the start goal is marked with this star sign, and the star state is marked with this star sign, and the goal state is marked with this diamond sign. So the graph is composed of a set of states, set of edges, and a cost function that assigns a cost to each edge. For our purposes, all costs are 1. And the solution cost of a particular problem induced by heuristic function or heuristic formula is as this. Basically, just after A-star search, the length of the solution path is the solution cost. The optimal solution cost is represented as here, is the shortest possible cost. And we define solution suboptimality as here is the ratio between the solution cost induced by H and the optimal solution cost. The best it can achieve is 1, which means the shortest path. And it can be 2 or 3. If it is 2, it means the solution induced by H is twice as long as the optimal solution cost. Right? Note that as long as the heuristic is admissible, the solution cost is the solution suboptimality is always 1. However, when we synthesize it, in general, the heuristic formula are not admissible. And heuristic synthesis. So how do we synthesize heuristics? So we define a space of heuristic formulae by a context-free grammar. We denote it by H, and we want the best formula from that space of formulas for a set of problems. So the sigma here is a speed up metric that we define down here. This epsilon is a function that returns how many states that are expanded on a particular problem by A star, guided by a formula, heuristic formula. And speed up is essentially a ratio between a number of states expanded by our baseline heuristic and the number of states expanded by some candidate or synthesized heuristic H on a particular problem. For baseline heuristics, we choose weighted Manhattan distance, and we have the script that automatically match an appropriate weight for the weighted Manhattan distance, such that the suboptimality induced by the weighted Manhattan distance is roughly the same as the suboptimality of the our synthesized H or some candidate H. So speed up essentially measures how much faster is our synthesized or candidate heuristic compared to the weighted Manhattan distance or baseline heuristic. So if it is equal to 1, then it means it's the same as Manhattan distance. If it is the higher, the better, right? The higher means our candidate heuristic is faster than the weighted Manhattan distance. And here is a some more illustration. Here is a video game map. The red states represent the states expanded, or the states that are in the closed list. The orange cells are the empty spaces, and the black cells here are the walls. Here is the closed list induced by Manhattan distance. The expanded cells are quite all over the place. And here is some synthesized heuristic. It's much better than the Manhattan distance, but it still expands. The search still gets trapped in some corners. And here is the closed list of expanded by the perfect heuristic. As you can see, it's a straight line from start to goal. There's no trapped corners or anything. Of course, it would be ideal if I can always synthesize a formula that represents exactly the perfect heuristic, but it's actually not feasible because we want to synthesize one formula that is portable across many problems, many search problems on a video game map. So that's some background here. Here's our problem setup. So for this thesis, we seek to explain a heuristic by asking the user to improve a heuristic. So we are essentially claiming that a human user's understanding of a heuristic formula is evidenced by their ability to improve it. And here is our definition of heuristic improvement. For a set of problem P, if there's just one problem in that set of problem, then we define heuristic improvement just by the number of nodes that are eliminated in the closed list by modifying that heuristic. Right? And we care less about the solution's suboptimality in this case, because it's just one problem. Right? But if there are many problems, then we just we mark the heuristic improvement by an average increase in speed up between the modified heuristic and the original heuristic. If the improvement fails, if there's no improvement. So essentially, if the modified heuristic expands more nodes or induces a lower speed up than the original, then we say the heuristic improvement has failed. Right? So I'll go over briefly some related works. So why formula synthesis? There are many previous works that train deep learning selectors or categorizers to select search algorithms given a search problem. However, deep learning models are not explainable because of its black box nature. The algorithms that the selector selects from are all previously published algorithms. However, the selection logic is hidden because the deep learning models are black box. And unrelated works on explaining formula synthesized. Right? There are, of course, previous works that synthesize algebraic formulae for getting multi-agent pathfinding, A-star single-agent pathfinding, and agent-centered search. Right? And they all attempted to explain synthesized formulae by breaking them down manually. However, this process involves human labor, and therefore we seek an automatic way to analyze a formula. And of course, there are works that automatically breaks down formula for explanation. Previous works automatically decompose and visualize synthesized programs, but none deals specifically with heuristic formula. Therefore, we seek to automatically decompose and visualize a formula for search. And as for explanation, sometimes large language models work. And previous work have proposed to apply large language models to explain synthesized formulae to human users. We have also tried applying large language models in our case. We have tried ChatGPT 4.0 and Gemini for purpose. However, the explanations are only correct for trivial formulas such as delta x squared or delta y squared. But the explanations for longer formulas tend to be very general, like they're just correct for any formula, or they're just incorrect. Like the explanation provided by ChatGPT might be completely the opposite of what the heuristic formula actually does. Thus, we need to propose other techniques. So that's some related works. Now I'll just talk about our approach. So there are 4 steps to explain given synthesized formula. First, we simplify the formula with several predefined read-write rules. There are very simple rules, like if we got 2 negatives, we just cancel them. If we get a square root with a square, then we cancel them, something like that, right? So we will not go over the simplification rules. And the second step is we convert all max and min operators to conditionals. So essentially in our context-free grammar, we have max operator and min operator. And in order to easily break them down, we need to first convert them to conditionals so that the condition and the subformulae are illustrated plainly. And then we can decompose the formula into subformulae and associate each with a region of the map. Well, of course, these will become more intuitive very soon. And then we visualize the subformula to map region association. That's our visualization. And I'll just explain how this works with a simple example. Consider we have a synthesized formula like this. It's max delta x delta y squared. And observe that depending on the condition, if delta x is larger than delta y is basically what max means, right? It returns the larger of the two. Either of the following subformulae is evaluated. So either delta x squared or delta y squared is evaluated. The condition evaluates to true or false depending on the location of the cell on the map. So for some cells on the map, it values to true and delta x squared is used. For some, delta y squared is used. Oh yes, they are all positive. Yeah, for the position on this, so for the inputs x, y, and x goal, y goal, they are all non-negative. They're all positive values. Yes, yeah. Delta x it's actually right here. It's defined right here. Delta x is just x minus x goal with the absolute operator right here. So formula essentially, like I just mentioned, it associates smaller formulae to map regions. So after breaking down max delta x delta y squared into the subformulae, the operator max essentially maps them, both of them, to govern different map regions, as illustrated here on this figure. So essentially, this is our visualization. We use arrows to point which subformula is assigned to which map region. So the yellowish region is governed by delta x squared, and the bluish region is governed by delta y squared. Essentially, when search starts, delta x squared will pull the search horizontally towards the goal. Therefore, it is expected that this interior of the C-shaped wall will be filled with nodes expanded, right, before search gets out. And then after the frontier touches the bluish region, then delta y squared will pull search vertically towards the goal location. Therefore, it will stick to this wall, and then after it gets over this wall, it will go straight to the goal. This formula was actually named the wall hugging heuristic because it induces a wall hugging behavior. And here we can see why it is called, why it induces wall hugging behaviors, because when search enters this region, delta y squared actually pulls it towards the wall. So it sticks to the wall, and then when it gets over the wall, it goes to the goal location, right? And inside of each of these colored regions, we also have a color scale that indicates roughly how the heuristic values change. So we can see that here in the interior of this yellowish region, the tiles are bluish. It means the heuristic values are smaller or decreasing as we move further horizontally to the goal, right? So that's essentially our approach. And here I'll go through a simple user study of how a user can use this approach to improve a given heuristic. We'll use this heuristic as an example. So first of all, we simplify it, but there's nothing to simplify. So we just convert all max and mins to the if conditional. Here we adopt the ternary conditional notation from the C language. So max delta x delta y squared is essentially converted to this. Max is converted to this operator. And then delta x squared is a subformula, and delta y squared is a subformula. And this is the figure from before. This figure here is the marks the nodes expanded. I also apply a color scale so that we can see the order of nodes expansion during the actual search. All right, so how can we, as expected, the interior of the C-shaped wall are all expanded. So essentially we want to modify the heuristic so that all these nodes are eliminated. So first of all, the user applied this, multiplied this constant 2 in front of delta y, so that this yellowish region is contained inside of this C-shaped wall. If we compare to this one, this is not contained, and this one is contained. The number of nodes expanded are not reduced by much, so we need to do more. And here's the slightly more interesting part. We introduced this delta wx as a new sub-heuristic. This is essentially the normal delta x operator, delta x subformula, but with this minus w at the end. W is the width of the map. So essentially what we're saying is we're fooling the search into thinking that the goal, instead of being here, it's actually all the way across the map, outside of the map, right here. Right? So that search will go towards the fake goal right here and accomplishing our objective of guiding it outside of this C-shaped region. And some nodes are eliminated. So the next step would be to amplify the effect of this subformula right here. And very easy way to do is to apply a constant, to multiply it. So we apply 4, and then all the nodes inside of the C-shaped region are eliminated. So we have improved the formula. And in summary, we have improved this formula to, we have modified this to this, and we have decreased the number of nodes expanded on that map from 169 to 77. So that's a success case. But now we want to apply this technique to actual video game maps. So here is a video game map from the Moving AI website. This map is based on a map from the game Dragon Age Origins. So there are 2 difficulties we encounter when applying this technique to actual video game maps. The first is that the actual video game maps are actually really large. So it's hard to visualize using our visualization techniques. So because, for example, here we can see the cells on the map clearly. However, here the maps is so large, it's hard for us to see any cells. And the second difficulty is that since we want to improve heuristic for a video game map, it means there are many search problems on this video game map. And we can only visualize one problem at a time. So how do we mitigate these 2 difficulties? So the first is we only let the user consider how to improve the formula for its worst pathfinding problem on a given map. So essentially, among all pathfinding problems, we pick the problem that induces the worst speed up or the most number of nodes expanded on that map. And then we only visualize that map and we let the user improve the heuristic just for that problem. And as for the second difficulty, we downsample the map. So essentially we turn the big map, shrink the big map into a smaller map. And hopefully by improving the heuristic for that smaller map, it's also improved for the original larger map. So here is our case study that was successful. It means it actually improved the speed up of the formula. So here is a synthesized formula for actually this map. But we have downsampled this map into this. This heuristic formula, I took this one from previously published work. And after decomposition, we have this subformula and this subformula, and we have 2 regions. One is this massive bluish region, and the other is this greenish region spread all around. And the adversarial problem selected on this map is as shown here. So essentially, what this indicates is that we want to eliminate all the nodes expanded essentially at this region here, right? But first of all, there's a problem because the user tend to, of course, the user is myself. I tend to first make the formula so that it's easier to understand. But here there's both a y component, so y goal involved, and an x involved. So the first thing I did was I turned this y goal to an x goal, and it has made the adversarial problem change into this one. It didn't do much, but this is the first thing that I did. All right. Oh, it's just the arrows that points this, that associates this formula to this region down here. Yeah. And yep. So that's the first thing, and then and here most of the regions, most of the nodes expanded are down here. So essentially, what we want to do is since the greenish region is associated with this subformula here, which guides the search horizontally towards the goal. We want to amplify its effect so that this greenish region can push the search outside of it, can push the frontier horizontally to the goal, so that it doesn't, hopefully, it doesn't expand the nodes down here. So that's what I did. I took off the square root sign here so that it's slightly more, so the effect of this operator is slightly more amplified. And then in order to further amplify the horizontal heuristic effect, I also added a delta X in front of it so that entirely this formula, after it's decomposed, either subformula would push the search horizontally towards the goal. So we have modified this formula to this formula here. And on the downsampled map, the speed up has increased on average from 1.49 to 1.51. And on the original map, speed up on average has increased from 3.84 to 4.19. So it's a successful case. On the downsampled map, we randomly generate 40 by 40 search problems. And on the original map, we randomly generate 200 by 200. By that, I mean 200 goals, and each goal has 200 start locations, that many search pathfinding problems. So these numbers are all evaluated. So the speed up on the original problem was evaluated on those 200 by 200 problems. And here is another case study. It's a not so successful case study. It's, of course, the map is also downsampled, and we have this formula here. And here, this formula was also picked from previously published work. And here is a somewhat difficult subformula because it involves both the horizontal component and the vertical component. And most of the state expanded are around this peninsula at the center of this map. Right? So essentially, we can see that when the frontier gets here, when it enters the green region, we want it to not to push so much vertically upwards. We want it to go horizontally towards the goal so that maybe it can get over this corner here to go into this peninsula. Yep.
Quickly explain the right graph. What is the color scheme there? What is the
Yeah, this figure here just shows the closed list, and the color scale here shows the order of node expansion of during the actual search.
First.
Yes, the colder colors indicate that it's expanded first, and the hotter colors indicate it's expanded later. So we amplify the effect of the delta X component, and it has sort of reduced the number of nodes expanded a little bit, but of course, the adversarial problem has changed. So so this time, most of the nodes are expanded here. We want to make it so that the search can go this way up. So we amplify the vertical components effect by applying this squared operator here to the delta Y. And we have gotten here. But this is kind of like a oscillation type of situation. We're doing one thing, but the adversarial problem is saying another thing. And it's, so we're kind of struggling here. Yes, myself. Yes. So the program only shows the user the visualizations, and the user is making modifications to this formula down here, and then submitting it to the program, and then the program would decompose the formula again and show the new decomposition plots. Yep.
One more thing you just mentioned to answer Russ's question. The program is also selecting the problem on which the heuristic misperformed.
Yes. Yeah. So the program does two things. One is that it demonstrates this visualization, and the other is it selects among from the 40 by 40 problems the worst problem in terms of speed up. So the adversarial problem.
Reasoning of the graph.
Yep. Yes. So, and here we have this 44.9, this weird constant here. The user believes this is map specific. So in order to make this formula more general, we take it off and we switch it to a squared operator here. And we end up with this formula here. So essentially we have modified this formula to this formula here. The speed up on the downsampled map has increased slightly. However, the speed up on the original map decreased quite much. And we suspect two reasons for the failure. One is that it's when modifying, the formula is getting more and more overfitted to the downsample map. And the other is the formula might be too complicated and the user could not modify it efficiently to actually accomplish what the user wants to do. So in order to solve these two issues, we observed that first of all, we need to make the formula synthesized simpler to understand, right? So for these two subformulae, this is definitely easier to understand than this. So the principle is we don't want to mix both horizontal and vertical components in a subformula. We want to either have just a vertical component or a horizontal component. Right? It's because people would understand it better. Yeah, and that's a great question, and that's the question we want to answer. If the size of subformula is constrained, will A-star search performance decrease? That's the first question we want to answer. Second, besides that, since we also have the previously I mentioned we also have we also convert the max and min operators to if conditionals. What if we extend the formula space with the if conditionals? So will that increase the A-star performance or decrease the A-star performance? So that's the two questions. Again, one is while constraining the subformula size hurt A-star performance, and the other is by adding the if conditionals into the formula space, how will it affect A-star performance?
Size and what is space?
Sorry, size of subformula is just how many operators there are in a particular formula. For this one, the size is 1 because there's just one, there's just delta x. For this one, the size is 1, 2, 3, 4, 5, 6, 7, 8. It's 8. Yes, max counts as 1. Yeah. However, the subformula will not include max because it's a branching operator. So so it does not include max. Therefore, max will not be counted. For the the subformula constraint limit is a hard limit. So essentially, it says subformula size cannot exceed that limit. Oh, you mean the number of subformulas? Is there a limit? There's no limit for that. So there can be. It depends on what the synthesizer synthesizes. Yeah. Usually, it's not that many. Usually, it's just 2 or 3. Yeah. So, so that's the two research questions we want to answer. We picked these two. The test bed are based on maps from these two games, Dragon Age Origin and StarCraft. And we pick 12 maps from Dragon Age Origins. We did it divided to 2 sets, Dragon Age Origin A, Dragon Age Origin B. In shorthand, it's DAO, Dragon Age Origins. Right? And from StarCraft, we also picked 12 maps. StarCraft set A, StarCraft set B. Right? And then just go through the notations very quick. So A means algorithm. The subscript means the constraint limit we want to impose, right? So 1 means the constraint of 1 subformula has to be less than or equal to the length of 1. And if there's no superscript, it just means there's no constraint on subformula size. And gamma means the grammar. If there's no plus sign here, it means the original grammar without the if conditionals. Plus sign means the extended grammar. It's just some notations, and here's our result. So multiple results on the 4 map sets. The y-axis is the speed up, average speed up. On the x-axis is the different combinations of constraints and grammar extensions. Multi-goal results. So multi-goal just means for each map, the problems we generate are just random. The goal locations can vary. So the normal setting, right? So any goal location is good. And for any goal location, there are a bunch of star locations, right? And we synthesize several heuristics for any particular map. And then we test the speed up on the test set. So that's how we get this variance, because there are many heuristic formulas synthesized for any particular map. And as we can see here, really the constraint on subformula size doesn't hurt the performance greatly. Although here we can see a general decrease trend as we apply more and more constraints, but it's not that bad. Unless if we have a constraint of 1, then the speed up really low. All right. So basically, as long as we don't have the constraint too low, it's all right. No, not with this is for the synthesizer. Yeah, yeah.
We didn't talk about the synthesizer.
Oh, the synthesizer was mentioned from previous work. We're just we're just.
What is the size of Manhattan distance?
Manhattan distance essentially is delta x plus delta y. So delta x is 1, plus sign is 1, delta y is 1. So it's 3. But as for delta x, as for Manhattan distance, you cannot break it down anymore, right? There's no branching factor, there's no max or min. So it by itself is its only subformula. So Manhattan distance will not be, well, it fits in this A3 setting because it's of size 3. But of course, if we do have Manhattan distance for the if we only synthesize Manhattan distance for the A3 setting, the speed up would be somewhere close to 1. Actually, it will be exactly 1. However, as we can see that the speed up is actually quite higher than 1. So for constraint 3, we can actually synthesize formula that are much better than Manhattan distance. They're not selected randomly. How we selected was listed in previously published work. The maps were shown previously. Some maps involve more corridors than others. Yeah. I would say they're the same. Yeah. Yeah. And since we have multi-goal results, we also have single-goal results. Right? For that, it just for any map, we make it so that there's just one goal at the center of the map. If the center of the map is covered by a wall, then it picks the closest empty cell to the center of the map. Right? And here we ran the experiments again. And this time for the single goal setting, the effects of constraints are more severe. As we can see, even with a constraint of 5, the speed up is quite lower than the speed up of the formula synthesized without any constraint on subformula size. And also, in this setting, it would seem that in the unconstrained setting with the extended grammar, the speed up is increased quite a bit as well. So for single goal setting, by extending the grammar, it's better. By not having constraints, it's better. But for our setting, when we want to improve a heuristic formula for a map in general, it's usually the multi-goal setting. So essentially, for our purposes, I think it's safe to say that by making the formulas more explainable, that is by making the subformula shorter, the performance is not hurt by much. So we can safely synthesize easy to understand formulae and make modifications to them. Yeah.
So the synthesis thing, it takes in
this map class, so DAOA, and then outputs a single heuristic?
It actually takes in one map and then outputs a single heuristic for one map.
Oh, heuristic is map specific.
Yes, it is synthesized. Yes, yeah. So it's the same way we did it from previous publication. So now, does it actually work, right? Will it make our previously failed case study better? So for this map, we have synthesized this heuristic. I picked it so that the constraint is 3. So the subformula size is no larger than 3. And this is surprisingly, the wall-hugging heuristic is the one that was synthesized. The subformulae are, of course, delta x squared and delta y squared. They're both of length 2 or size 2, right, lower than 3. And this is the adversarial problem that was picked for this downsampled map. Essentially, the start location is right here. The goal location is right here. Essentially, it's expanding all these extra nodes that we don't want it to expand. So we essentially want to either make this region larger, the bluish region larger, so that it covers the start location and pushes the search slightly to the right so that it gets over this small corner right here and goes straight to the goal. Or we want to add an horizontal component to this to the delta y squared, right? And we picked the former. We actually slightly increased the value of the x component by multiplying by 1.5, and it has reduced the number of nodes expanded. And we thought that's actually good enough, so we terminated the process. And actually, the speed up on the downsample map increased, and the speed up on the original map also increased. And this 5.32 was actually higher. The speed up was actually higher than the speed up of the previously synthesized heuristic without constraints. So actually, with computer and human collaboration, we're able to produce simpler formula that has better performance than just computer alone, right? Yeah, I provided 1.5. The machine provided this formula right here. Yeah. Mm-hmm.
This is like a weak computer, I guess. You give it like 100 years, obviously you can't beat it.
Maybe, but from the empirical studies, we find that the more time we give the synthesizer, the longer the heuristic tend to grow, and the more map specific it tend to be. So, well, it's not a bad thing as long as we don't want to apply previously synthesized formula to some other new map. Yes. You mean synthesize one formula for all maps? We tried that, yes, but it's from our experience, the formula are not as simple as this. It's usually longer. Yeah. Well, actually, we can. It's probably part of the future work to compare human computer collaborated formula with just computer generated formula for across multiple maps. I believe it's a great future study. Yeah. So for future work, obviously there can be more user study. There's just one user, which is myself. Yeah, and for this thesis, I only applied this technique for offline A-star search. And of course, we can apply this also for agent-centered A-star search. It's actually just agent-centered search. And since agent-centered search is really close to reinforcement learning, we thought it's also applicable for reinforcement learning. Say we synthesize some formula that computes the initial expected values for each state, and then we can visualize it, and so on and so forth, right? And also we can do this human-computer collaboration development for bioacoustic generative models. So actually, in biology, they not synthesized, they hired physicists to come up with formula that can produce bird sound to solve the data, the lack of data problem. Right? But what if we use computer to generate those formulas for bird sound or bat sound or any sound, right? And that could be better, right? And also to use large language models. Previously, although we have tested that the large language models cannot be directly applied to explain synthesized formula. However, it can give a good introduction to the trivial formulas. So maybe we can use large language models to explain subformulae of short size, that is. And for this thesis, I have gone through our idea of formula decomposition, and I have gone through our visualization or heuristic explanation, and I have done several case studies of iterative formula improvement, and I've showcased our empirical work. And that's everything. Thank you for listening. Is there any questions? Yeah.
So, at the beginning, you were saying if I have formulas, they are easily explainable. That was, I don't think that is true, because formulas, they can become really complicated. And
yeah.
Maybe it is easier, but in the end, I guess we just run experiments to understand them. So using neural networks as opposed to formulas, again, I don't know anything, but seems like not really an explainability issue. Maybe there are other factors. Like, could you tell me, like, why would I prefer a formula? I don't believe this explanation. Are there other maybe composition, heuristics, or maybe they're just smaller, so why more generalizable?
The belief is that, so previously I mentioned neural networks to select previously published algorithms for search problems, right? So the belief is that eventually computers can develop their own algorithms, maybe through formulas or even write their own programs. So we're heading towards this direction, which we believe can, in the end, be better than previously published works.
But I think world not simple. Artificial science here, it is much trivial. Why not just find best answer? Why not just get a faster computer? Solid.
Because we want to, because there are certain things that humans are really good at and computers are not so good at. I mean, eventually, maybe computers can be good at everything, but right now there are many things that our computers are not very good at, that our humans are good at. So we want to take the best of both. Yeah. Yeah, definitely.
I guess in all these experiments, maybe the hope is we'll replace humans with an LLM later. So it's like a neurosymbolic thing.
Yeah, but maybe eventually LLMs would be very similar to a human. Then we can just, plug in all sorts of algorithms to an LLM and then create general intelligence. But I believe there's still there's still a long way to go from now to that stage. Thank you.